11.3 Mountains. You're really growing, aren't you? How many times has someone made a comment like that to you? Have you ever thought that the same kind of comment could be applied to a mountain? How do mountains form? Which ones are still growing? Why do they stop growing? These are the kinds of questions that scientists ask as they try to solve some of the mysteries related to Earth's crust. In Chapter 10, you learned how sedimentary rock is formed. A lot of sedimentary rock has formed at the bottom of ancient oceans from shells and marine creatures. These shells have gradually settled to the bottom and over many, many years have compressed and built up to form layers of sedimentary rock. In other areas, sedimentary rock is made of sand, gravel, and mud. How does sedimentary rock turn into mountains? The activity described in the margins will help you visualize the process. Figure 11.23. Can you see the layers in the rock of this mountain? These are exposed sedimentary layers in the Rocky Mountains of British Columbia. Sedimentary rocks that are placed under slow, gradual pressure can either fold or break. As you have seen, rocks that are pushed against one another can cause earthquakes and volcanoes. These occur when there is relatively rapid movement. Geologists explain that rocks can fold if they are hot enough to act like a bendable plastic. It is important to remember that where a volcano exists, the rock beneath Earth's surface is hot enough to melt into magma. Where mountains are formed, the rock is only hot enough to bend. Can you see the folded rock layers in the photo in figure 11.23? Study the diagram in figure 11.24 to see the fold lines in the rock. This is what you imitate in the activity with the modeling clay. The upward or top part of the folded rock is called the anticline. The bottom of the fold is called the syncline. Over time, both of these can erode, but the folded layers still indicate what has happened. Can you identify the top of figure 11.23 as an anticline or a syncline? So 11.24, these are the main types of folding action in mountain formation. So like the tips of the waves is the, looks like the syncline, and the bottom of the wave, or the trough, is the anticline. Make a hypothesis about why mountains continue growing and why they stop growing. Hint, think about what is happening in Earth's crust. What does a young mountain look like? What does an old mountain look like? Mountains that are jagged at the top are young. Mountains that are more rounded are older. Think back to the rock cycle in chapter 10 and try to identify another difference in appearance between a young and an old mountain range. Look again at figure 11.23. Would you describe the Rockies as an old or a young mountain range? Some of the peaks in the Rockies are so high that they are snow-covered all year. If you think that the Rockies are a young mountain range, you are correct. They are one of many younger mountain ranges in the world, with the Himalayas in India being the youngest and the highest. The top of Mount Everest in the Himalayas, like you, is still growing taller. The Laurentian Mountains in Quebec are not as high as the Rockies. They are an older mountain range that is in the process of being worn down. Sometimes the rocks in Earth's crust are too brittle to fold. When pressure is exerted on them, they break, forming a fault. Many different kinds of faults are created when the rock is too brittle to bend. As you know, the best known example of a fault is the San Andreas Fault in California. In 1906, the San Andreas Fault shifted 6 meters from side to side near San Francisco, causing a huge earthquake. Figure 11.25. This photo of sedimentary rock layers was taken in the Rockies near Lake Louise, Alberta. Figure 11.26. Compare this map with your map of earthquakes and volcanoes. Most of the western coastline of North and South America are areas where rock surfaces are pushing against each other. As well as moving from side to side, faults can move up and down or vertically. Vertical faults are called normal faults if the rock moves down, and reverse faults if the rock is pushed up. Mountain ranges are often the result of more than one kind of action. See figure 11.27. Mountains created as a result of both folding and faulting are described as complex mountains. The photos of the Rockies show folding in the rock layers and faulting in places where the layers are broken away. Figure 11.27, fault movement. You have a normal fault, you have a reverse fault, after erosion, and after erosion. So you have the normal fault, and then you have the after erosion picture, and then you have the reverse fault and the after erosion picture. Layers of the earth. For a long time, people have wondered about what might be under the ground to cause earthquakes and volcanoes. Jules Verne wrote a book called Journey to the Center of the Earth, which described what he imagined the center of the earth would look like. We are still not able to travel into the interior of Earth. In fact, it is too deep for us even to drill for test samples. The earthquake waves that are discussed earlier in this chapter do give us some evidence of what might be inside the Earth. The earthquake that happened in Kobe, Japan in 1995 registered on a seismograph at the University of Manitoba because P waves travel right through the center of the Earth. S waves did not register. We know that P waves can travel through liquid and that S waves cannot. Therefore, we can hypothesize that Earth's center must be liquid. Both P and S waves actually change their speed and direction as they travel into the interior of Earth. Scientists have constructed a model of the interior based on the information from these seismic waves. See figure 11.28. 11.28. Primary waves bend when they hit the outer core, and secondary waves are stopped completely. Because primary waves are bent, there is an area where they do not come through on the other side of Earth. This area is called shadow zone. Geologists have learned about the interior structure of Earth from these two kinds of waves. Earth is composed of an outer layer called the crust and an inner layer called the mantle and a central portion called the core. The crust is very thin under the ocean. In some places, it extends only 5 to 6 kilometers down. Under some parts of the continent, the crust reaches a depth of 60 kilometers. You could compare the inside structure of Earth to an egg. The crust is the eggshell. The mantle is like the white of the egg. The inner and outer core are represented by the egg yolk. The cracks that you make in the shell of a hard-boiled egg could be the faults in the rocks that are causing earthquakes to happen. Just below Earth's crust, the mantle made of rock material has the consistency of taffy. At a lower level, the mantle is solid. Earth's core is made of nickel and iron. The outer core, just below the mantle, is liquid. The intense pressure of all the layers about the inner core cause the inner core to be solid, in spite of its high temperature. Figure 11.29 shows the temperature of the various layers of Earth.